Hello, I'm Professor Von Schmohawk, and welcome to YU. So far in our algebra lectures, we have studied linear functions, quadratic functions, polynomial functions, and rational functions. In the next several lectures, we will introduce two additional functions. These closely related functions are the exponential functions and logarithmic functions. The functions we have studied so far have been algebraic functions. Algebraic functions are functions that can be constructed using only a finite number of algebraic operations such as addition and subtraction, multiplication and division, and powers and roots. On the other hand, exponential and logarithmic functions are members of a class of functions called transcendental functions. Transcendental functions are said to transcend algebra since they cannot be expressed in terms of a finite sequence of algebraic operations. Instead, the exact value of a transcendental function can sometimes only be calculated by adding an infinite series of decreasing terms. The more terms that are added, the more accurate the calculation becomes. Exponential and logarithmic functions are essential tools used not only in scientific fields, but also in calculations used in business, finance, and medicine. For example, exponential functions are used in banking and investing to calculate compound interest or return on investments. Exponential functions are also used to model changes in population of humans and animals, as well as archaeology and anthropology to calculate radioactive decay used in carbon dating. Likewise, many types of measurements use logarithmic functions. Examples of this are the decibel scale, which uses a logarithmic function for measuring the intensity of sound, and the Richter scale, which uses a logarithmic function to measure the intensity of earthquakes. Likewise, the pH scale used to measure the acidity of a solution is also logarithmic. In this lecture, we will start by understanding how exponential functions work. In the functions we have studied, the variables sometimes contain exponents. And so far, these exponents have been constants. But what if instead of being a constant, the exponent was the variable? Functions with variable exponents are called exponential functions. Exponential functions typically consist of a constant called the base of the function with a variable exponent. And the function's base must be a positive real number other than 1. So as an example, let's calculate a few values for the exponential function f of x equals 2 to the x power. When x is 2, 2 squared is 4. And when x is 1, 2 with an exponent of 1 is 2. When x is 0, since any base with an exponent of 0 is 1, 2 to the 0 power is 1. When x is negative, any number with a negative exponent is equal to 1 over that number with the same positive exponent. So 2 with an exponent of negative 1 is equal to 1 over 2 with an exponent of positive 1, or 1/2. Likewise, 2 with an exponent of negative 2 is 1 over 2 squared, or 1/4. 2 with an exponent of negative 3 is 1 over 2 cubed, or 1/8. And so on. We saw that this exponential function has a value of 1 when its exponent's value is 0, which is also true for all exponential functions. As x takes on larger positive values, this function's value increases exponentially and decreases exponentially as x takes on larger negative values. Since over its entire domain, this function's value increases as x increases, this is said to be an increasing function. So let's see what happens when we choose base values other than 2. If we graph the exponential function f of x equals 3 to the x, we see that this function's graph also passes through the point 0, 1, since any base with a 0 exponent is 1, but increases more quickly for positive x values and decreases more quickly for negative x values. For larger base values, the graph still passes through the point 0, 1, but the rate that the graph increases and decreases becomes even more extreme. Likewise, for smaller base values, the rates of increase and decrease become more gradual until when the base has a value of 1, the function's graph becomes a horizontal line. However, since a horizontal line is the graph of a constant function, a base value of 1 is typically excluded for exponential functions. For base values less than 1, the function grows smaller for positive x values and larger for negative x values. Since over its entire domain, this function's value decreases as x increases, this is said to be a decreasing function. As the base value becomes smaller, the exponential function decreases more quickly. However, although the base of an exponential function can be arbitrarily small, it cannot be 0, since the base of an exponential function must be a positive number. So why is the value of an exponential function's base limited to only positive numbers? For instance, why can't the base be 0? The problem with a base value of 0 becomes apparent for negative values of x. As an example, let's consider an x value of negative 2. Since any number with a negative exponent is the same as 1 over that number with the same positive exponent, this is equal to 1 over 0 squared, or 1 divided by 0, whose value is undefined. Therefore, base values of 0 are not allowed. But then why are negative base values not allowed? For instance, what would happen if the base was -1? If x had a value of 2, then the function's value would be -1 squared, or 1, which would not be a problem. However, when x has a value of 1/2, this would cause the function's value to be -1 to the 1/2 power, or the square root of -1. But since no real number is equal to the square root of -1, this function would have no real solutions. Since there are an infinite number of x values like this that would cause this function to have no real solutions, negative base values are also not allowed for exponential functions. So we have seen that exponential functions consist of a base that must be a positive real number, other than 1, raised to the power of a variable such as x whose value can be any real number. As one example, we saw the exponential function 2 to the x power. However, the exponent of an exponential function can be more complicated than just the variable x. So let's look at a couple of examples. Some exponential functions may have a positive or negative constant added to the exponent. For example, consider the exponent x plus 2. Adding 2 to the exponent does not change the graph's shape, but it causes the graph to be shifted 2 units to the left. Likewise, subtracting 2 from the exponent causes the graph to be shifted 2 units to the right. Another possibility is for x to be multiplied by a constant. For example, we could multiply x by 3. Multiplying the exponent does affect the graph's shape, causing the graph to horizontally shrink or expand. In this case, multiplying x by 3 causes the graph to shrink horizontally by a factor of 3. And as we have seen, a positive or negative constant could be added to this exponent. For instance, subtracting 2 from x before multiplying would shift the graph 2 units to the right. And distributing the 3 to the terms in parentheses, this exponent could also be written as 3x minus 6.
In the beginning of this lecture, we introduced exponential functions and said that they were essential tools used in many fields, including business and finance. In the next lecture, we will see how exponential functions were developed in the 17th century as a way to calculate a new idea called continuous compound interest.